Man, these are all too working out too nice. Okay. All right. Yeah. Let's try that. See if we can't. Okay, this will be interesting. Okay, how about that? What do y'all think? Okay, so we run the nth term test first. If we run the nth term test, we take the limit as n goes to infinity of this. What would happen if we let n go to infinity on that? Get infinity over infinity? If you do L'Hopital one time, the top is going to go to 1. The bottom is going to be like a product rule derivative, but you're still going to have 4 to n powers, so this is going to go to 0, all right? Is it geometric? Is this geometric? The 4 to the n is geometric, but it's this n minus 1 that's not geometric. Okay? So not geometric? Telescopic? Can't factor. I don't think we can. Not harmonic. So compare maybe? What would we compare this to? Negative 1 over 4 of the n? 1 over 4 of the n? Just think about what happens when n gets big. When n gets really big, might help if you look at it like this. That's the same thing, isn't it? When n gets really big, what is this getting really close to? 1, right? I mean, essentially, you take the limit as n goes to infinity, this goes to 1. So this is really acting like a 1, and this one is acting like a geometric series, right? 1 over 4 to the n. So why don't we compare it to the geometric series 1 over 4 to the n? The reason I'm not going to use negative 1 is because it's not alternating. It's just... So let's try that. Let's do, compare it to sum n equals 1 to infinity of 1 over 4 to the n. I need some sticks because I'm getting the same people participating. I need everybody participating. And Michelle requested this, right? Last week you said you liked it when I do the sticks?
No.
I think you told me the opposite of that, didn't you? Yeah. No way, Michelle. I just pulled your... I'm serious. That's so funny. Yep. Okay. So, Michelle, we are comparing it to this. And what type of series is this? Geometric? Okay. If this is geometric, can you tell just by looking right now if it converges or diverges? So can you tell what R is? Like, it would take some manipulation, but at the end of the day, have an idea what R would be? 1/4, right? Because you could eventually rewrite this 1 over 4 to the n, and then because it starts at 1, you try to make this look like n minus 1, but this will be your R, right? So that's 1/4, and that's, what does that mean this geometric series does? It converges, right? So we are comparing this to a convergent geometric series. Now, if we do the limit, still going to work. The thing is awesome. It's going to be pretty awesome. I don't want to tell you not to use the limit because it would work here. So let's do the limit.
I hate that, man. I hate when things work.
Limit as n goes to infinity of the n minus 1 over n times 4 to the n over 1 over 4 to the n. Be careful because you're doing that sequence, right? That sequence over that sequence, and then you're going to take the limit. So do y'all see what I mean? It's going to work out nice. This is going to flip up. So when it flips up, this 4 to the n comes on top over 1, so that's gone. And you see the 4 to the n's? These are gone. And now all you're left with is n minus 1 over n. And if you take that limit, you get 1. Yes?
So earlier you said we like split them both up and you had like n minus 1 over n.
Uh-huh.
You said that went to 1.
I said we were trying to figure out what to compare it to, right? So when we look at this initially, you're like, wow, there's a lot of things going on here. If you were to rewrite this as n minus 1 over n times 1 over 4 to the n, you could do that, right? Because that's just put them together, you'd be back up here. This right here is n gets big. This is behaving really like a 1, isn't it? Infinity over infinity, L'Hopital, basically that's headed to 1. So this isn't really doing much in terms of like affecting this piece. Now as n goes to infinity here, of course, this does go to 0, but this part really does not contribute much later, like as you go further out.
Okay.
So I'm going to compare it to that and not look at that at all. And it turns out it's fine. It just turns out this limit turns out to be 1. That's a positive constant. We're in business. I need to.
No, I thought you picked that one.
Well, I wanted to do this one first. There was another one after it that I'm pretty sure we're going to be messed up on. Man, I have my doubts on this one too. Okay, let's try this. Let's see what happens with this one. I still am not promising you that the limit won't work, okay? Okay, what about this one?
You can use it 1 over 2n, or 1 over 2 to the n as the comparison.
1 over 2 to the n, where are you getting that from?
So 2 to the n over 4 to the n is 1. It would be
2 to the n over 4 to the n.
It would be 1 to the n, which is 1 over 2 to the n.
Okay, so I think I see. So as n gets big, this stuff out front really doesn't matter.
Right.
Okay?
Right.
So it's really looking like 2 to the n
Over 4 to the n.
over 4 to the n, which you're saying as
1 to the n.
2 over 4 to the n. Is that what you're saying? And that's 1 over 2 to the n. Okay. What do y'all think of that logic? Yes? Yeah? Okay, let's try it. So if we're going to compare it, we're going to compare this to some n equals 1 to infinity of 1 over 2 to the n, or 1/2 to the n. Which way do you want me to write it? 1 over 2 to the n or 1/2 to the n?
That one.
That one? Okay. So that okay?
We had the previous.
Okay, so this is another geometric, right? This is geometric. What does it do? Converges because P is, not P, R is 1/2, which is less than 1, right? So we've got a geometric series that's convergent. All right, do we want to do the limit? What is that? Well, I don't know. Do we want to do this limit? It's probably pretty nasty. It's probably pretty nasty. Let's try it. Let's just see what happens. That thing's been so good to us. We don't want to just bail on it now. So I know some of you know I've been kind of into woodworking and stuff, and I don't know. I posted a YouTube video of a saw I modified or something. I didn't realize that goes out to everyone, but oh well. Anyways, I was in my garage the other day and I was listening. Like I always have the radio on or something, streaming, and there was this song I've heard it 1,000 times, but I actually listened to the words, and it's some country song. I don't know what it's called, but the girl's talking about like, oh, obviously she has an ex-boyfriend that's, moved on, and she's like, I hope that you look into her eyes and, you're driving down the road and you just feel all this joy and all this stuff. No?
Yeah,
and then at the very end she says, and then I hope she cheats. and then it's like you cheated on me, and I'm sitting there, I'm like, God, this is a nice song. She's moved on, she understands, she hopes he's happy. I'm like, this is wonderful. And at the end, she's like, no, I hope she cheats on me. I think it's called I Hope or something like that. It was. Why am I talking about that? Oh, because I don't want to break up with the limit yet. It's been so good to me. I'm not quite sure I want to leave it behind here at this point.
It's supposed to be N goes to 1?
No, it's not. I was thinking about this song. I'm sorry. N goes to infinity. Okay, so limit. Let's try and do that flip thing. And when we flip it, things are not as nice as they have been, no? Because when I flip it, all that happens, this becomes a 2 to the n up here like that over 1. And so maybe I could do this 2 to the n plus 2 to the... So I'm basically distributing. Here to here, here to here. So here to there is that, right? What's this times this? 2 to the 2n. So look, these have the same base, right? So add the exponents. N plus n? 2n. So this is 2 to the 2n over 3 plus 4 to the n. Right, that's what we've got. So we definitely have infinity over infinity, and we could start trying to run our L'Hopital. Those derivatives are going to not be fun, though. Do you all agree? Okay, so maybe a limit comparison would be better. No promises. I'm going to say stand by. We may get back together, okay? I just need a little time away. Just need some... Okay. So I need to compare it, right? So if I'm going to compare it to this, then what do I need to show? I want to show that this is what in relation to this? Smaller, because this one converges. So I got to make sure this one... Is that true? That this is less than or equal to 2 to the n? Is that true? That doesn't look much better, does it? Does not look much better. So I'm going to try something a little different. You ready? This is what we want to show, right? I'm going to move this over here. How about this? 1 plus 2 to the n over 3 plus 4 to the n less than or equal to 2 to the n over 4 to the n. That's just me rewriting it. Right? That's just me rewriting it. That's what we started with to begin with. When we chose to use this, it came from this idea. Okay, now let's try and cross multiply maybe. We cross multiply, we're going to get 4 to the n times 1 plus 2 to the n less than or equal to 2 to the n times 3 plus 4 to the n. So what do y'all think about that? Anything we can do?
Distribute.
We could distribute.
Divide both sides by 2 to the n.
We could divide both sides by this, by 2 to the n. Would that help?
That would reduce one side, so you're not having to multiply out the right side.
Okay.
Distribute and then subtract.
Distribute where? Just distribute? Let's try distribution. Let's just see where it takes us. If we distribute, we have 4 to the n plus 2 to the n times 4 to the n, and then less than or equal to 2 to the n times 3 plus 2 to the n times 4 to the n. Isn't that what we would get? Like that? Right. So this and this are the same, aren't they? Okay, so that can go away. And what about this? 4 to the n less than or equal to 2 to the n times 3. No. Not true. Right? How could you convince yourself of that? How about we divide both sides by 2 to the n now? Divide by 2 to the n? 2 to the n. What does the left side become? 2 to the n. Right? 4 to the n over 2 to the n. That'll become 2 to the n. Is that smaller than the right side? What's the right side? 3. Well, it's smaller when n is 1. But after that, it's over, right? The left side gets bigger. So this is not true. What does that mean? Nope. We tried to compare it with something that converged, right? Our inequality didn't hold. That means nothing. It means nothing. Okay? In order for this comparison test to work, we have to compare it to something, we have to know what it does, and then the inequality has to hold. Then we can come to a conclusion. If the inequality doesn't hold, we have to make an adjustment. We have to tweak something. Okay? So you ready for this adjustment? Watch. Let me see. I think I'm going to try this. No promises. I might go back to that old girlfriend, the limit. Okay? So let me do this. I want to compare it to something else. How about 1 over 2 to the n plus 1? Okay, so what is my thinking here? It's a little bit bigger, right? Still geometric, still converges, right? It's a little bit bigger. See the bottom here. Let me show you what my idea here is. The top is basically acting like 2 to the n. I want to try and treat my bottom like this. Okay, so do y'all agree that this top is essentially this top, right? Essentially. And then the bottom here, because this is a 3, it's kind of close to 4. If I replace it with the 4, then I can put those together, can't I? 4 to the n plus 1. Right? I could have chosen any number, but I chose 4 on purpose because my power on the bottom is 4. Let's see, what is this? Sum n equals 1 to infinity of 2 to the n over 4 to the n plus 1. Agree? Now, what type of series is this? Geometric, right? And are we going to converge or diverge? Converge, because we're going to have 2 over 4 to the n, which is 1/2 to the n. So this is convergence, because our r eventually, if we worked it out algebraically, would give us a 1/2. Right? Okay, now, let's try again the comparison, but my inequality is going to look like this now. And then 2 to the n over, see, 4 to the n plus 1. Does this help at all? What I'm trying to get y'all to see is the thought process of trying to come up with a comparison. I need that to hold. Does it help? Can you tell me on the left or right which denominator is bigger? Which is bigger? This one or this one? This one's bigger, right? So if this is bigger, this fraction should be smaller, right? What about the numerators? That one's bigger, but they're essentially the same, right? I don't think that inequality is going to work out. I think if I do the cross multiply and subtract, I think I'm going to go to the same place. What I'm trying to get you to see is that you have to think about what's happening within the inequality and make adjustments in order to try and make the inequality work. So how could you make this side bigger than this side and still have convergence over there? How? You have to make the denominator smaller, right? Or the numerator bigger. But you can't go past the convergence, because if you go past convergence, then your divergence, then the inequality flips. I think I'm going to leave this one as an open. This is a good thinking problem. I think we could go with the limit. I think the limit one is a good one. But I don't want to. I want to see if we can get it with a comparison, but I want to leave it to you to see if you can figure it out. That seemed like a fair little, I don't give a lot of bonus questions, but that seems like one.
So this will be a bonus in the final then?
Just a little bonus. Just a little bonus. Yes.
Is there ever like equations you can compare it to that it works at the end, but the comparison was just too far off from the original? You know
What do you mean it works at the end?
Like say we picked something and we worked it all out
And it worked out, like this inequality was true.
Right.
And you knew what this did.
Right.
Okay.
Okay. Is there ever like this one is too far away from that one where you can't use it?
No, as long as you know that this one converged and you're able to show that inequality is true, you're done. Doesn't matter if these things look completely different. As long as the inequality would be the hard part of that, I think.
I think, so how does this, again, can you tell me again how this one correlates with this one? Like how you got to the n over 4 plus 4 to the n? And how you were able to extrapolate that from the original series?
It's, again, we're trying to see what does this look like that I can actually compare to that would be something I know, right? So we already tried 2 to the n over 4 to the n, and we got something at the end that didn't work.
Right.
So I said, okay, let's try something else. Instead of treating this like a 3, let's treat it like a 4, and that way I can put these together and make it 4 to the n plus 1. And then on the top, I just said take the 1 out, right? But maybe make that a 2 and make that a 4. Yes?
I was going to say, since our comparison for convergence failed, could we just try just a random series that diverges and do the divergence test? And
Or test it to see, like flip the inequality?
Yeah.
Okay, so the question is, maybe because we haven't been able to find something, maybe this diverges. And so if we can compare it to something that diverges and show the inequality the other way, then we would be done, right? I agree, we could do that. The only hesitation I would have is just that I'm pretty sure this converges. Because when n gets really big, this and this don't matter. And so you're essentially geometric. So I think you would have a hard time to find something to compare it to that would actually diverge there and the inequality holds. All right? Are y'all not going to be satisfied unless we finish this, or should I give it to you as a bonus?
Stop it. Stop it right now, Gina. Bonus, please.
Okay. Let me see what I have next in my notes. Maybe
Do you want this by next class or something? Or?
I want it in 5 minutes.
Oh.
No. Next class, yes.
Bingo.
Yeah, you know what? Let's. I want to get to a few more problems. Let's leave this as open. But I'll try and finish it up if no one turns it in next time. I'm not saying that that's like this super hard problem. It's that you need to go through the exercise of trying to find something. Okay, that has to be an exercise that you're doing. Right? Just keep trying different comparisons until you get something where the inequality will work. Let's go back to this. Sum n equals 1 to infinity of a constant over linear. Okay, what type of series did I tell you that was essentially? Harmonic, right? Constant over linear. And I told you all harmonics will do what? Diverge, right? Now I'm going to show you that with the limit, with the comparison test with the limit. Okay, so let's say we have something like that, okay? And I come over here and I compare it. And let's say I compare it to 1 over n. What do I know that that does? That diverges, right? Diverges why? It's harmonic, or you could say it's p series with p being 1, in which case it diverges. So this diverges, yes? Now, if I do the limit on this, and I do the limit as n goes to infinity of that, which is going to be a constant over linear over 1 over n, what can you tell me about that limit? It's what? It's always going to be a number. Look, n goes up here, 1 here, right? This would cancel. So look, this top right here is a constant times n, which is just going to be some linear function in n. And then on the bottom is some linear function in n. So when you take the derivative, right, because you have infinity over infinity, when you take that derivative that first time, all you're going to get are the coefficients in front of your n's, which will be a constant, and that'll be positive. So this will equal some constant, and it will be greater than 0, which means that you will have whatever one does, they both do, right? What did this one do? Diverged. So if you don't like that, if you're not following that, what I'm saying is if you replace it with some number, and on the bottom you have any linear function in x, or in n, okay? Constant over linear, then when you get to this step right here, you're going to have 7 over 3n plus 1. Now that looks like 7n over 3n plus 1, and we know that when you do that limit L'Hopital that first time, you're just going to get the two coefficients in front. That will always be a positive number greater than 0, right? I mean, positive number, not infinity. So therefore, they're both going to diverge. Yes?
What if it started that constant is negative?
Pardon?
The constant was a negative? Like it was negative 7 instead of 7?
Remember, the condition was that we had that the two series we're comparing are positive, right? Is that what you're asking? Yeah.
Would there be a way to like pull out that negative? To make it?
Yeah, if it wasn't alternating, right? You're just saying it was negative, you could just pull the negative out,
And then just do the test.
compare those, and then if it would diverge, and then it's negative out front, right? So it's still diverging just to negative infinity instead of positive infinity. Okay. I want to just at least in the last 15 minutes get into the next section, other convergence tests. What's wrong?
15 minutes?
10 minutes.
Oh, 10, well, 12.
Sort of.
10 minutes. Oh, no, you'll like this one.
That's what you said about the last one.
You liked it, though.
Did I?
Yes. All right. We have conveniently stayed away from alternating series. So this is the second from the bottom. So if you have your series n equals 1 to infinity of -1 to the n times a sub n. So here's something to keep in mind. We know that when it comes to alternating, we can either start negative or positive, right? don't pay too much attention to this being n or n plus 1. It's just as long as it alternates, starts either positive then negative, positive, negative, or it could go negative, positive, negative, positive. Doesn't matter, as long as it's flipping. And this is the part that changes sign. This is the part that doesn't, this right here never changes signs. All right? So if you have an alternating series and you want to know if it converges, look at the test. What is the test saying? Converges if what? Converges if a sub k is greater than or equal to a sub k plus 1, and also the limit as n goes to infinity of a sub n equals 0. Okay, these are two separate things that we have to look at. The alternating series test is super easy to use. It's actually a really nice test. So let's go to one of my favorite examples of this. Sum n equals 1 to infinity of negative 1 to the n over n. This is, yes.
That says limit n goes to 0.
I keep on messing this up. No, it's infinity. It's infinity. Yes. So when you look at that, you can pretty much throw out a bunch of the tests that we've done already, because all the tests that we've done already have assumed that these pieces in here are positive. Okay, unless this is geometric, but it's not, right? Because the n is not a power. It's down here. So it's an alternating series. Do you all agree? So if it's an alternating series, we can run the alternating series test, which means we need to first show that this thing is always bigger than or equal to that. That means that we need to show that our series is decreasing. Our sequence is decreasing. So what I'm going to do first here is I'm going to rewrite this so that it looks like this piece that alternates times this piece, which is our a sub n. So our a sub n is the piece that has been detached from the alternating part of the sequence. Do you see that? Okay, so we're looking at a sub n is 1 over n for us here. So what does this mean to show that it's decreasing? Do you remember when we did bounded monotonic? And I said this is going to come back? It's back. We have to show that a sequence is decreasing. So I need to show that this sequence right here is decreasing. Want to show a sub k is greater than or equal to a sub k plus 1. So what is a sub k? If that's a sub n, what's a sub k? 1 over k. Is that bigger than or equal to 1 over k plus 1, right? Is that true? Yeah, that's true. You could cross multiply. K plus 1 is bigger than or equal to k. Cancel the k's. 1 is bigger than 0. That's true. So is it decreasing?
Yes.
Yeah, decreasing. Okay. What's the last thing I need to show? That limit of the limit as n goes to infinity of a sub n is 0. That means all I have to do is take this limit of that, let n go to infinity, and see if it's 0, which it is, right? So that's my second thing here. Put it up here. So for 2, the limit as n goes to infinity of 1 over n equals 0. Check. Both things have checked. What does that mean? It converges. Okay? So do you remember like the nth term test, right? The nth term test is a test that we run in the very beginning, and we say if the limit of the inside here goes to 0, what does that tell us? If the limit of the inside of there goes to 0, what does that tell us? Nothing, right? When you get to alternating series, if you take the negative alternating part out, and you look at that thing and take the limit and it goes to 0, along with the decreasing gives you convergence. Yes?
So this is kind of like, I don't know how to explain it or how I do it, but it's basically if you took an absolute value
Okay.
of that, and if it was convergence, or if it equals 0, it converges, right?
If the absolute value of a sequence converges, sequence.
So that's the difference.
Yeah, that's the difference. That was back when we were in 8.1. And then once we got to 8.2, we started doing series, so that would not apply. Okay, so you still have 5 minutes. So I'll start the next chapter. No, I'm just kidding. Okay, so let me give you one more of these as an example for you to work through, or for us to work through. All right, does that series converge or diverge? Okay, so what's the first thing you notice about it? It's alternating, right? -1 to the n. Alternating. So the first thing you should be thinking is alternating series test. All right? It's the first thing you should think. So you have to show two things, right? Alternating series test. You have to show, first of all, that it's decreasing, which means a sub k is greater than or equal to a sub k plus 1. If you want to use a sub n is greater than or equal to a sub n plus 1, you can use n's. The k is a dummy variable here. And then you have to show the limit as n goes to infinity of a sub n, that is 0. So what is the a sub n for us here? What is the a sub n? The n squared over n cubed plus 1. That is our a sub n, right? It's the part that's not getting alternated. Do you all agree that number 2 is going to be easy? If I take the limit as n goes to infinity of that, I'm going to get infinity over infinity. I'll do L'Hopital, I'll do it again, and I will get 0, right? So that's going to check out. I just have to show the decreasing part. That might be a little harder. What are our two options when it comes to showing a sequence is decreasing? We have two options. We can just go straight after the inequality. What would that inequality look like if I tried to set that up right now? K squared over k cubed plus 1. That must be greater or equal to k plus 1 squared over k plus 1 to the third plus 1. I'd have to show if that's true, right? Is that true or not? That might be a little messy. Would you all agree? Could we do it? Sure. I mean, algebraically, it's a lot of work, but we could probably cross multiply and expand and do all that. But what's the other way we can show things decrease? Show the derivative is negative. So can we treat this? So I'm going to say, hold on, I don't know about that. If I look at this as a function, which I can, because that is a nice polynomial over polynomial, then I could just take the derivative of this real quick and see if it's negative. What interval would I be considering? 1 to infinity, right? Okay, so let's take derivative of that. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So there's my quotient rule. The derivative of the top is, not derivative, the top cleaned up is 2x to the fourth plus 2x minus 3x to the fourth all over, well, does the bottom matter? What can you tell me about the bottom? It's always positive, right, because you're squaring something. So that's going to be positive down there. So that's not really going to contribute. The numerator is 2x minus x to the fourth over a positive number. So is that negative? When I plug in 1, what do I get? Get 2 minus 1, which is positive, right? But after that, right? What happens after that? Now it's going to be 2 times 2 is 4, but then that's going to dominate it, isn't it? If you don't like that, you can pull an x out. And you can look at it that way. So when x is 1, right? When x is 1, you've got that times 2 minus 1. That's going to be a positive number. But once you get past that, right? If x is 2, this is always going to be positive, and then this will always be negative. So our derivative is negative, right? Eventually. And so it's decreasing. So we've satisfied both conditions. What does this series do? Converges. Okay. I would expect now for you to try your homework for 8.3. Not quite ready for 8.4 yet. We still have more to talk about. Do you remember in the beginning of the semester when I was saying we need all the time we can get? This is what I mean. We're bogged down in chapter 8, which is pretty normal. All right, homework on 8.3. Bonus question, if you'd like, you can turn it in next time. Yes?